All right, how's it going, everybody? We are here on Monday of week 10. This week, we're going to be talking about chapter 8, which is confidence intervals. We just hit chapter 9 last week, which talked about our hypothesis testing. And really, hypothesis tests and confidence intervals are going to be the two essential final topics of the semester here. This is what we're going to discuss for the last 6 weeks of the course. So we got our introduction to hypothesis testing last week. We're getting our introduction to confidence intervals this week, and we'll see lots of scenarios in which we want to apply these ideas in the next 5 weeks after this here. Um, Confidence intervals do a little bit of a different job than hypothesis tests do. They're going to help us make estimates rather than make decisions. But it's very true that there is a lot of overlap in the thoughts that we have about the two. And it's also true that we can kind of do the job of a hypothesis test with a confidence interval and vice versa a little bit. We'll talk about that a little bit tomorrow, a little bit next week. Um, so, the purpose of a confidence interval is when we want to make an estimate about a population parameter. Remember, the population parameter is like a statistic that is something associated with an entire population. So, this would be something like the average height of all adult males in the United States, population parameter. But we only have access to the information associated with a sample, right? So, it might only be that we've sampled 100 adult males. What we want to do is we want to make the best judgment that we can possibly make about the actual true population average from only our sample information. What we know is that samples can vary, so it's not necessarily the case that when we see a sample that that's directly representative of the full population. So what we want to take into account when we look at a sample and try and pass judgment on an entire population is we want to acknowledge that that sample could have included some variability, and so we don't want to necessarily overstate what we think that we know about the overall population. So let's look at a couple examples just to kind of see what we mean by some of these statements here. We're not doing examples, we're just stating examples as to what type of information we want to know here. So first things first here in example 1, suppose we discover a new species of insect and we would like to estimate the average weight of a member of the species. We collect a sample of 45 members of the population and we find that the sample's average is 121 grams with a standard deviation of 9 grams. What our goal here is to say the true average weight of all of these insects out here of this species is blank. What we don't have is we don't have information about every single individual in the population. What we do have is just the information about 45 members of the population. So our goal is to make a statement about mu, but all we have access to is X bar, right? We want to know the population average. We only have the sample average. So I'm asking the question here, kind of our leading questions is, what claims can we and can't we make about the true average weight of the species of this insect? And what I think we can and can't say here is, let me give myself a little more room here. Our best estimate for the population average, mu, is our sample average. And I'm just going to type X bar because it's annoying for me to type that out right there. So our best guess is that the population average is 121 grams. So what claims can't we make? We don't necessarily think that our sample average of 121 grams is exactly correct. We know that every sample may experience variation. Right? Every sample is going to be a little bit different than other samples that are taken out there. So we don't want to overstate what we know here. What I do know is I do know that I have a pretty good guess for the value of mu. I could just guess the value of X bar. But what I'm kind of thinking here is I'm not certain that that's correct. I might be a little bit off. So rather than saying I think mu is this one number, We're not going to make a one number estimate. We're going to say it might be anywhere in this entire interval surrounding that one good estimate number. X bar is a really good guess, but it could be off by a little bit. So I'm thinking it might be something a little bit bigger than X bar. It might be something a little bit lower than X bar, but it should be near whatever our sample average is. We should be able to form a interval around X bar where we are confident that the true value of our population average mu must actually live. Right? So what we can state and what we can't state here are, we think that 121, since it's our sample average, is a pretty good guess for our population average, but we don't necessarily think it's exactly correct because we know that there could definitely be some variation within the sample that we drew. The second scenario here that I want to look at, the second scenario I want to look at here is one that we're going to cover a little bit more in detail tomorrow. A pollster would like to determine how much support a certain ballot measure has 1 week before the election. She polls 84 people about whether they support the measure or not, and 48 say yes. So what this pollster is not interested in necessarily is just 48 people's or 84 people's opinion. What this pollster is interested in is the entire population's opinion about a certain ballot measure. This pollster wants to know about every person in the city that's going to be voting in this thing, but trying to take information from just 84 people to try and get a bigger picture of what's going on in the entire city out there. So some things that I might say right here, by the way, are I'm identifying here that it looks like we sampled 84 people and that the number of successes was 48. And therefore, our sample proportion would be 48 divided by 84. Right, so it looks like from this sample proportion that we just took right there, we're finding our p hat, our sample proportion, to be 0.5714. About 57% of people in the sample say that they're in support of this ballot measure. But again, we're not 100% sure that that's exactly what our overall population proportion is going to be. It might be in the city. Maybe we actually accidentally just got a sample that had a little bit more support or a little bit less support than what's actually true of the entire city overall. So I still think it's good for us to estimate a point estimate at a single point, our estimate of what the entire city's proportion of support is to be near 57%. But we know that this sample could vary a little bit. Maybe it's really more like 55%. Maybe it's really more like 60%. It should be probably something near to 57%. I think that's a good place for us to center our estimate. But we're kind of thinking to ourselves that it could be some surrounding values. So what we're really trying to come up with today is not one value to estimate a value, but entire interval of values to make an estimate of one value here. So what claims can we and can't we make? We think our best estimate of the true population proportion is our sample proportion, 57.14%. However, samples can vary. All right. So, same statements as before. We want to state what we think we know, but we don't want to overstate what we know here. Our best guess for our population proportion would be our sample proportion, 57.14%. But we know that samples can vary from the overall population. It might be that we got a little bit more support or a little bit less support that is overall representative of the total population. And so we don't want to just claim that we think the answer is 57%. We want to say it's something near 57%. We're pretty sure of that. What we want to measure is how far do we really think that we're actually going to be from 57%. So what we want to do today is find a way to compute not just our estimate, not just our sample average or our sample proportion. We can already do that. What we want to do is compute what boundaries we should give for an interval around that value, around that estimate, so that we can say that we are at a specific level of confidence certain that our true population parameter is contained within this confidence interval. All right. So again, our goal here is to make statements about a population parameter. Pretty typically, it's the population average or the population proportion, although we will see some other ones in a couple weeks. We're always going to use sample information to make our best guess. We're going to say we have a little knowledge. Let's try and make the best guess that we can with our little bit of knowledge about the entire population as a whole. Since our sample can always vary a little bit, we know that we don't want to overstate what we know, and that's why rather than coming up with one number to estimate our population parameter, we're going to come up with a whole interval to estimate where our population parameter might live. You should picture this like on a number line. So, what factors should be associated with our confidence intervals? What things are going to change how large or small our location of our confidence interval? So these statements here are going to be about a population average. Proportion, we could easily substitute any of our associated phrasing. All right. So the first thing I want to say here is what features should we think of about our confidence interval? Well, first things first. Our best guess for our population average, mu, is our sample average, x bar. So we should center our intervals there. Where we are confident that the mu value lives, we should center it at x bar because we kind of think that's the most likely location for where mu is going to be. So when we build our interval, we're going to put the value that's at the very middle of our interval to be our sample average or our sample proportion. If the population has a large standard deviation, then the interval should be wide. And that's because we know that our samples can vary from what the typical result might be. So if there's a lot of variation, a lot of deviation associated with given samples, then we might have to say, well, even though we got this x bar, it could have been some value way over here because there's lots of variation in the data, and it could be that our sample varied quite a bit from what we would think of as a typical scenario. So when we have large standard deviations, we should end up having those associated with very large confidence intervals. Which is not necessarily a great thing, right? That says we have a very broad span of where we think the value lives. What would be very good for us would be to have very, very narrow confidence intervals, because then I can say, aha, I know really, really accurately what mu is. I know it's between this value and this value, and they're really close together, so I have a really good idea of where it lives. When we have huge confidence intervals, that's just like me saying the sentence, I am confident that the true average height of adult males is between 5 foot tall and 7 foot tall. That's not a very strong statement, right? That's a huge confidence interval, really, really wide, 24 inches wide in that example right there. And it gives us basically no information. Of course, we already know that the average height of adult males is between 5 feet and 7 feet tall. We would really like narrow confidence intervals. Those give us lots of information. We're really pinning down exactly where we think our population parameter is with narrow intervals. So when we have large standard deviation, that reduces our confidence about where our true population value is going to live because we know that our sample could have been varying quite a bit. On the other hand, if our population has a very small standard deviation, then we're much more confident that our sample's values are representative of the overall population values. And so we should end up getting a much narrower confidence interval if we know that our values are not deviating from average by very much. The more individuals that we sample, the more confident that we are that our sample estimate is reflective of the population. Maybe I'll change it to sample average. All right, so the larger and larger our sample gets, the more information we have, the more certain that we are that the average that we got from our sample is representative of the average of the population as a whole. And so what that should result in for us is if we have a very large sample size, then we have a ton of information, right? We're very certain that our X bar, that our average is very accurate. And so with large n's, with large sample sizes, we should get those very desirable small confidence intervals, reflecting the fact that we have a lot of information. On the other hand, when we collect very small samples, then we know that there could have been a ton of variability in that sample. So if we're only collecting a sample of like 8 insects to measure their average weight or something like that, our sample average could be quite a bit off from the overall population average. And so we're going to get very large confidence intervals, which is a pretty weak statement about what we know out there. But again, the more information you have, the better we can predict. And so our confidence intervals get narrower, saying we have a much narrower view of where we think mu might live. That's more information. It's a better prediction. Finally, if we want to be very confident that our interval contains the true population average or proportion, then the interval needs to be wide. And this, by the way, sounds counterintuitive the first time you hear it, so talk through this one with me. If you want to guess where a number lives, and you want to be really, 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 really sure that your interval of guesses captures that value, then you want your interval to be very wide. Unfortunately, wide intervals don't give us lots of information, right? Because that's, again, like me saying, oh, a true average adult male height is between 5 feet and 7 feet tall. That's a very wide interval, and it provides us relatively little information, right? That didn't pin it down very much at all. If we want to be very confident that our confidence interval captures the true population average, then we need to make it bigger. You got to cast a bigger net to be more sure that you're going to catch a fish. That's our analogy here, right? On the other hand, if we're not too worried about making sure that our interval truly does capture the population average or population proportion, then we could make it narrower, but we might have a greater chance that we actually missed the value of interest in our interval. It might be that we form a confidence interval over here, but that the true population average was somewhere over here. We maybe missed it, which is kind of a bad thing. But then again, that's just going to be associated with our lower confidence that we're going to capture that thing. So there should be some degree of confidence associated with this. We're going to make statements that sound like form a 80% confidence interval, meaning form an interval in which you are 80% sure that the true population average lives in that interval. If we're only needing to be 80% sure that it's in there, then we can make it very narrow, because that means to me only 4 out of 5 samples should return a confidence interval that contains the average. On the other hand, if we want to be super, super, super sure that our confidence interval does contain the value of interest, mu or p, then we need to make that extra wide. If we're going to make a 99% confidence interval, it should end up getting much wider, because we need to be more certain that we're going to capture the true population average in it. Again, if you want to be more sure that you're going to catch a fish, you need to cast a wider net. Right? If we want to increase the confidence that we capture the value of interest, we have to make a wide confidence interval for that. So large amounts of confidence are associated with large confidence intervals. Low amounts of confidence are associated with smaller confidence intervals here. So kind of what we're kind of feeling out here when we say this, if n gets big, then our confidence interval gets small. And if sigma gets big, our confidence interval gets big. And if our confidence gets big, our confidence interval gets big. What we're really describing here is where each of these parameters is going to be located in an equation. What I know is that if I have a numerator in a fraction that's big, the overall value of the fraction gets big. I know that if I have a value in the denominator of a fraction that's big, the overall fraction gets small. And these are some related statements to what we just saw going on over here in our bullet points over here. So we're going to come back to this list at the end. This will be kind of our wrap up as coming back to review this guy right here. I want to do a bunch of the math, and then we're going to come back to revisit these statements once we've actually seen some computation here. So let's walk away from this, but again, I'm going to come back to the screen as our last screen of the day right here as sort of our summary of what we've seen today. So forming confidence intervals. So let's look at an example. What we're going to do today is oh my gosh, I'm sitting on my kind of wrong, wow, okay. It's funny, I'm on my wrong screen right here, and it actually captured everything I wanted. There we go. Now I'm happy with what our screen actually looks like here. Oh, that's really funny. I didn't even notice we were on the wrong screen there. All right, so forming confidence intervals. We're going to build and inspect our first confidence interval based on an example about ACT scores here. All right. And again, you should be able to see that up in our upper right-hand corner, you've got exactly the same information here. So when I scroll away from this, we can still see what we're interested in over here. And we're certainly going to be using Excel, just as we've been doing, to form some computations here. And by the way, as you guys have been seeing me do in the last couple weeks in Excel, I've been sort of like building like a table of values and like referencing them relative to each other a couple times. That's going to be a super useful thing for us to do today in exploring how does our sample size affect our confidence interval? How does our standard deviation affect our confidence interval? It's going to be really nice for me to be able to just modify one number and see our computations change here. So realize that that might be a satisfying thing for you to be doing here as well. So here's our scenario. Suppose a school wants to estimate the average ACT score of its students. The school samples 40 students and finds their average ACT score to be 24.5. The ACT scores in general, nationally, are known to have a standard deviation of 2.8 points. What we would like to do is determine a 90% confidence interval for the true average ACT score of the students at this high school. Let's state what we do know and what we don't know here. Um, and importantly, stating what we don't know is equally as important as what we do know here. So, a couple things that I'm seeing here. It looks like we have been given that the sample size is 40, n is 40. It looks like we've been given that our sample of those 40 students, our x bar, is 24.5. And it looks like ACT scores are in general known to have a standard deviation of 2.8. Now, I'm going to try and avoid having this discussion here today because we're going to have this discussion tomorrow. But exactly like we saw last week, we want to make this distinction between scenarios in which we know sigma versus scenarios in which we know S. Standard deviation of the population or standard deviation of just the sample. In this case right here, I'm stating that generally in the entire population, ACT scores are known to have a standard deviation of 2.8 points. I could have alternatively said the school samples 40 students and finds their average ACT score to be 24.5 with a standard deviation of 2.8, in which case you would have interpreted 2.8 as the sample standard deviation if that were the case. That would have been S. But here, I'm going to do the same thing I did last week, and we're going to be talking about Z instead of T because sigma is known. So it looks like sigma was given to us here as 2.8 points. Mu is unknown. Want to estimate it. With a 90% confidence interval. So, and I know that we don't quite know what that means yet. We're going to build all the pieces right now, but it's important that we always kind of lay out our information that we have available to us. So I'm trying to estimate the value of mu. What I want to know is where really is mu? I've just got only my sample information. Oh, by the way, sorry, I should say here. So we're not trying to estimate the like the overall, because we're not sampling from the entire country. We're only sampling from the high school. Therefore, our population is just the people that took the ACT at this high school. So we're trying to form a confidence interval for the true average ACT score of the high school students at the particular high school. We don't know what this overall average is. We've only sampled 40 students that took the ACT at this high school, but there's maybe hundreds of students at this high school that took the ACT. So we're trying to take a small bit of information and push it onto the broader population. So where should our interval be centered? And let's just say here, our best guess for mu is x bar. All right, so that's going to be our estimate. And just to throw a vocab word at you right here, this is referred to as a point estimate. The reason that we call it a point estimate instead of just an estimate is because the entire purpose of a confidence interval is to be an estimate, but it is an interval of estimates. rather than an estimate of one value, right? So 24.5 is our guess for mu, but we're also going to be making a statement in a second here that's going to say like 24.3 isn't a bad guess either, right? So an entire interval of estimates versus a single point estimate, right there is the distinction. So when we say a point estimate, we mean a one number estimate versus an interval estimate right there. So our point estimate from mu is x bar. And remember, we're trying to make statements about mu. But what we know is that we don't necessarily think it's exactly x bar. We know there could be some variation that we got from our sample. So we want to say, well, it should be some value around 24.5. What we now want to compute is how far around 24.5 should this be? So let's ask the question, what distribution do our samples of 40 students follow? Well, what's the distribution of one student going to be? We're actually really not sure here. We've been given this. We weren't even given that these were normally distributed, in fact, right here, right? We just know that we're taking samples of larger than 30 students, so our sampling distribution should be normal. So I can't even make my statement of distribution for an individual here, but I do think I know how our groups of 40 students are distributed. This should be where our sample average of 40 people is distributed normally because we have more than 30 in our sample size. Our average, we are estimating this guy right here. Our estimate is going to be our 24.5. And our standard deviation here is like our sigma over root n, right? But really, like, that should be mu in that slot right there, right? So, like, it's kind of like we don't really know that. But this term is going to be important. Standard error term. Remember that this is our measure of distance, or let me say that as size. So that's going to be a term that's really of interest to us, that sigma over root n. Remember that that is the measure of the size of a standard deviation. Now, what we're going to want to know is what does this 90% really mean to us? So by the way, we're going to come back. Sigma over root n is going to be a critical part of our computations here. I'm kind of waffling on calling this 24.5 what I want to call it, right? Because the bottom line here is that that's actually slightly incorrect. We truly don't know what mu actually is, so I can't really say where this distribution is centered. We're guessing that mu is x bar, but then we're just using our guess to make an estimate about our guess. That kind of doesn't make any sense, right? So this information here is kind of bad. But this information here is really good. This is going to be very practical for us. We do know sigma, we do know root n, but we don't know mu, so I don't really want to say much about this column right here. Sigma over root n is our measure of one standard deviation's distance for a sample average of 40 students, and that's going to be really practical for us. So the next question here is really important, and we're going to have to play with this one a couple different times here. We'll play with this one quite a bit today here. What number of standard deviations bounds the middle 90%, right? So what we're asking here is if we want to be 90% confident that our interval captures the true population average, and if the samples that we collect follow a normal distribution, then it should be the case that the middle 90% of the values in our x bar distribution are exactly the ones of interest to us. So what I am interested in capturing here is the middle 90%. If there's 90% in the middle, then that should be the case that there is 5% in each direction on the tails. And so what I might be interested in is knowing where is this value that's right over here. We're going to call these some very special locations, right? These are going to be what we call critical values right here. There are cutoffs between being in the middle 90% and not being in the middle 90%. You should notice that because this is a symmetric distribution, because our left and right sides of a normal distribution are exactly the same, whatever z value is here is the exact same z values over here, but this one's just negative, right? This is always centered at 0 on a z scale right there. Our standard normal distribution is always centered at 0 with a standard deviation of 1. So typically we refer to this as z star. right? Put a little asterisk because it's power right there. And what we know is that this guy over here is going to be the exact same value of z. It's just negative because it's on the left-hand side over there. So that's kind of how I would draw my diagram associated with this guy right here. And so if I want to find where these locations exactly are, why do I use 5%? Good question right there, Jose. So if the middle 90% is what we do want to capture, then what I know is that 100% spans the entire left-right distance, right? 100% of all of our area goes from left to right. So if I am interested in the middle 90% being captured, that means there must be 5% that is in this left tail and 5% that is in the right tail, so that together these three groupings, these three subdivisions of our interval, accrue to all 100% of all of our probability that's out there. So where I'm going with this, really the other question should be, why do we care? Not just where did they come from, but why do we care? The reason why I am interested in these guys is because I want to know where are z star and negative z star. Well, what I should be able to do is to use a inverse normal calculation to find out. I know how much area I think is to the left of each of these two values right here now. So I should be able to come up with their locations. So z star should be defined such that the probability that our z value is to the left of z. So let me talk our way through this here. If we were to take a sample and find how many standard deviations our sample is, that would be z, the number of standard deviations of our sample is. If it's going to be less than z star, that means it's going to be to the left of z star here. And we can see that there is 90% plus an additional 5% of our area is to the left of z star, right? For our negative z star, what we're seeing here is that only 5% of the area is to the left of z star. So the probability that we take a sample and see that its number of standard deviations from the mean is less than negative z star should be 0.05. So what I can do is I can go, and I'm going to go into Excel right now, and I'm going to see if I can compute these. Now, what we're remember our little helpful guesser to ourselves here, not a guess, I know this is true. The number that is associated with z and with negative z star are the same. It should just be positives and negatives is the only thing that should be changing over here. So I'm going to find z star and negative z star. What? Oh, don't put an equal sign in front of it. What? Stop putting, oh man. It's not okay with that minus sign in there. Okay, let's go ahead and find z star here. So what I'm thinking here is the upper bound of my 90%, my middle 90%, is actually where 95% of the area is to the left. Again, notice if I am interested in this location z star right here, then because it is the upper bound of a 90% confidence interval, that actually means that 95% of the area is to the left of it, because there's 5% in each of our tails as well. And to the left of z star does include one of the two tails for 5%, plus the entire middle 90% for a total of 95%. So what you're going to see me do down here in Excel now is I'm going to do my norm.inverse. I know that I have a probability of interest, 95%. What I want is what z value gives me that. How many standard deviations is associated with 95% of the area to the left? Well, norm.inv wants my probability, that's a 0.95. It wants my mean, and since we're in a standard normal distribution, since every time we're ever talking about z, always when we talk about z, we are talking about the normal 0, 1 distribution. Z is always distributed normal 0, 1. Right? Z. That is just definition of what we mean when we're talking about z. Average is 0, standard deviation is 1. So coming back over here, I've got my mean is 0, my standard deviation is 1. And this is our number of standard deviations away that we are if we're at that z star location. Let's do the same thing real quick for negative z star just to verify that we are going to get these symmetric answers right here. If I do norm.inv, my probability now is 0.05 because only 5% of the area is to the left of negative z star. Our average is still 0, standard deviation is still 1. And notice we're getting the exact same number, but just the negative version of it right there. So it looks like I'm getting 1.645 and negative 1.645. So we're really close to being able to build this confidence interval. Actually, we have all the information that we need now to build our confidence interval. So let's see how we can put these pieces together. All right, so we found those z values in Excel. So how do we form a confidence interval? So what we want to do is we want to form an interval. Right? If we're going to form an interval, this is sort of the structure of all of our intervals. If we're going to form an interval to estimate something, our point estimate is going to go right at the dead center, and then we're going to have an upper bound and a lower bound. The distance from the point estimate to the upper bound and the distance to the lower bound are going to be equal to each other. And we refer to these distances as the margins of error. A margin of error is just one of the two distances. It's not like the whole width of the interval. The width of the interval is twice the margin of error because it's one margin of error above to one margin of error below down there. All right. So what we want to compute then is if we can compute what is our point estimate, and if we can compute a decided margin of error, then that will tell us where our upper bound and lower bound are. Right. So we want upper bound and lower bound. What do we need to get an upper bound and lower bound? A point estimate and a margin of error. All right. So we know that our point estimate, that's our x bar equals, what did we say, 24.5? So really the big thing here is we need to know how do we compute our margin of error here? Well, what we've decided is that for a 90% confidence interval, what captures the middle 90% is going 1.645 standard deviations above and below the mean. Get this way out here. Say that again. Since we want a confidence interval in which we are 90% sure that we're capturing the true population average here, then since we want a 90% confidence interval, we found that we may see samples that are as much as 1.645 standard deviations from average. Then, let me spell that correctly. our size of standard deviation is, that's our sigma over root n. Our standard deviation given to us up here was our 2.8 points right there. 2.8 is our standard deviation. 40 was our sample size. Oh no, come on. I don't know what you're doing. Stop doing this to me. I don't. Okay, so what is the size of one standard deviation here? It's our 2.8 over root 40. 2.8 divided by the square root of 40. I'm getting 0.4427. So let's go ahead and use this information now that we have to make our estimate here. What I'm kind of thinking to myself here is we want to go start at 24.5. And how far up might we be interested in observing values here? How far up do we think our population average might live? It might be bigger than 24.5, right? What I'm thinking here is should be a measure of number of standard deviations times the size of a standard deviation. So here we're going to say, let me back this up so I can. So our general structure of a, seriously, you can do it to me again? So our general structure of all confidence intervals is always going to be exactly like this. We're always going to have a point estimate, our central location that we're estimating. We're always going to have a plus or minus indicating that we're capable of going in either direction. We might be above, we might be below our true population average. We're going to go up and down by our margin of error, right? So this is exactly our picture that we're looking at right here. We're going to get our point estimate, and we're going to add to our point estimate our margin of error, and we're going to subtract from our point estimate our margin of error. That will get us to our upper and our lower bounds right here. So in this case, our point estimate here is x bar, plus or minus. My computer just going to freak out right now. Computer, are you with me? Can we do this? Okay. X bar is my point estimate. My margin of error, how far should we go from X bar? Well, what I'm seeing here is we should be measuring a number of standard deviations. We're going to go 1.645 standard deviations away because of that's our representative of our 90%. But I need to know how large one standard deviation is, right? So this says from your point estimate, go 1.645 standard deviations above and below, because 1.645 is our number of standard deviations associated with our middle 90%. But I need to know how far, what distance 1.645 standard deviations actually is relative to ACT scores. You should notice that X bar is in terms of X. It's in terms of ACT scores. Z star has no X information at all. Z stars are very generic, just number of standard deviations with no context. I would like to take my number of standard deviations and multiply it by the length of one standard deviation in the context of the problem. So this is where I'm going to do my sigma over root n. So by the way, this right here, this is it. This is our confidence interval formula right here. Our margin of error is z star sigma over root n. Our point estimate is x bar. So in this case here, we're going to get our 24.5 plus or minus 1.645 times 0.4427. And let's go ahead and compute this value, state our conclusion, and then we'll state our conclusion also in words here. I'm going to go hit my calculator up again, and I've got my 0.4427 times 1.645. That's given me 0.7282. And I can now do my plus and my minus right here. So 24.5 plus 0.7282, 24.5 minus 0.7282, 24.5 plus 0.7282 is 25.2282. It's an interval, so I'm going to give that as a parenthesis and then some comma right here. And we've also got 24.5 minus 0.7282. And that's going to give me 23.7718. All right, so here we go. This is our very first confidence interval of it right here. All right, so we're going to state a verbal conclusion about this guy. But what we've just done is we've formed a confidence interval estimate for the true population average of the average ACT score of all of the students at this high school, based on only 40 of the students at this high school. Our average is centered at our sample average of 24.5, but based on the fact that we wanted to be 90% sure that we were going to capture that thing, not necessarily 100% sure, but not only 50% sure, which by the way, I'm going to diagram that for us in a minute right here. We decided that about 23.8 to about 25.2 is where we are 90% confident that the true average of the entire high school is going to live. This is taking into account the known potential for variability in our sample here and saying, listen, that sample might have varied a little bit. Your sample is still a good estimate, but it might have varied a little bit. So here's the interval around our estimate that we think is a little bit more appropriate. So let's state a verbal conclusion here, and then let's draw a diagram here. We're going to do kind of two things for stating our conclusion. How do we interpret what, oh, I see what I did right there. So our verbal conclusion here, how am I going to decide what, or how am I going to state what I even mean by this? We are 90% confident that the true average ACT score of all ACT takers at this high school is within the interval 23.7718 25.2282. Right? We are 90% confident that the true average ACT score, that's mu, of all ACT takers at this high school is within this given interval. And maybe we could say here, this is based on a sample of only 40 ACT takers. Right, so we're saying here, we wanted to make a statement about the entire population. We just sampled a little bit of the population, and we're trying to make the best guess that we can about the whole population, but again, without kind of overstating what we know here. Right? So how do we interpret this statement? What do we mean when we say we're 90% sure that the true population average is contained within the interval? What this means to me is there is 90% of samples of 40 students will result in a confidence interval that does capture mu, (10% of samples of 40 students will result in a confidence interval that does not capture mu. And I'm going to draw a little picture here to help us out with this one. So here's kind of what's going on out here. Out there in the world, there's a bunch of different values out there. Mu. I'm going to say here, but we don't know where mu is. Right, this is on some x-axis out there. The true population parameter of mu exists technically, but we don't know it, right? We don't really know where it is, right? So what's going to happen here is we're going to go out there and we're going to take a sample of 40 students. I'm going to call this sample 1. Maybe this is the sample that we just took. And maybe what happens when we take that sample is we find an X bar that technically is a little bit less than mu, but again, we don't know that when we take it because we just straight up don't know mu. But maybe our X bar lands about right there, and maybe we get a confidence interval that looks like this. Well, it looks to me like this confidence interval that we've formed here, I'll draw it like this. Our confidence interval does contain the value of mu. Look, it's sitting right there. There's mu right there. We got it in there. So this is a good confidence interval. We were 90% sure it contained the value of mu, and it turned out that it did, right? And so what might happen here is we might take a bunch of samples, and they're all probably going to have that little bit of variability, right? So here's maybe my next X bar, and notice maybe this one's actually a little bit larger than mu, but this is still a good confidence interval. It still contained the value of mu sitting right there. And so maybe we take lots of these samples. And maybe sample three was a bit more extreme out here, and maybe we just like barely actually still captured that value of mu in there. It's barely in our confidence interval, but it's technically in there, right? So we've captured the value of mu. So what we kind of think might happen out here is that 10% of our samples are probably going to be wonky enough that they're probably going to miss the value. They're probably going to not capture that value of mu out there. So what might happen here, if we're forming 90% confidence intervals, then that might mean that there's a 10% chance that we actually missed that value of mu right there, right? And notice that mu in this case is sitting right there. So in this case right here, our sample average was far enough away from mu that our confidence interval missed, right? Right? So every time we're making a confidence interval, we're estimating where we think a true population average is going to live. It might, it's not necessarily the case that our X bar is going to hit it exactly. That's what my thick bars are intending to indicate right here. But notice these first three intervals all contained the value of mu. But this fourth one down here had a kind of extreme enough sample average that it looks like it missed it. So this is one of the 10 then that we would say missed that interval. So as with all things in statistics, we're never certain about really anything out there. But we do want to say what percent confidence we are certain about a statement that we're making. So when I come back up to my example up here, this interval might end up not actually capturing the true average ACT score in this high school. We're only 90% sure that the actual high school's true average is actually in this interval because we built a 90% confidence interval. If we want to be more confident, watch what happens if we change our confidence. If we want to increase our confidence from 90%, then we're going to be capturing even more of the middle, more than 90%. That should make this z value here get pushed even further to the right. So the z value is going to get larger. Z star is going to get larger. And notice that z star down here, if z star gets larger, then our margin of error gets larger. So we're going to get wider confidence intervals if we increase our level of confidence out there, or vice versa. If we decrease our level of confidence, we'll get smaller intervals. So let's go look at some what happens when we change some of these parameters here to see what's going to be different, right? So we want to say, how are each of these parameters influencing the confidence interval's size and location here? If we change the sample average from 24.5 to 22.5, maybe I'll just kind of type out a phrase here. It's the center of the confidence interval that we're talking about changing here. So, I know all I'm going to conclude right here is the two parts of every confidence interval are the point estimate and the margin of error. Here, we're talking about changing x bar, which is the point estimate. We're not changing the margin of error. So the width of the interval should be the exact same, but it should be that we have slid the whole thing to the left. It used to be 24.5, it's now 22.5. So I might say before, we were getting 24.5 plus or minus, what was that value? 0.7282. Now we're getting 22.5 plus or minus 0.7282. All right, so these intervals should be the exact same width because we didn't change the margin of error term. We only changed the point estimate term, so we should have just moved our interval to now be centered at a new location right there. This is our least exciting change we can make. Let's see the much, much more exciting changes we can make. The original sample size was 40. What if our sample size was 30 or 50? This one I think I'm going to need a little bit more room here. And what I want to do here is let's make 3 columns. N equals 30, N equals 40, N equals 50. What I know that N affects is our margin of error. The more information that I have means I should be able to pin down our average into a slightly smaller span than before. On the other hand, if I have less information, then I have less confidence about where this thing lives, and we're going to get a much bigger interval associated with that guy. All right? So what I know here, in all 3 cases, that x bar is 24.5. Let me just make these statements. Right? I didn't change my point estimate, so that's still 24.5 for all 3 cases. I also didn't change my level of confidence. %95 confidence still means that my z star value of interest is going to be the 1.645. That hasn't changed either, although we are going to change both of those things coming up right here. That's still, I haven't changed that part of the problem here yet, right? What has changed when we changed n is we've changed what our length of one standard deviation is, right? So what's happened now is our sigma over root n has changed. So now I'm getting 2.8 over root 30. I'm going to get a 2.8 over root 40. And I'm going to get a 2.8 over root 50. And we are going to use each of these values, our new standard error terms, as our length of one standard deviation. And that's going to affect the size of our confidence interval. So 2.8 divided by the square root of 30, 5.1 or 0.5112. 2.8 over square root of 40, 0.4427, that's the one we've already seen. And 2.8 divided by the square root of 50 is 0.3960. So I can now form 3 new confidence intervals associated, or 3 confidence intervals overall here. For all 3, remember that we're looking for our x bar plus or minus z star, the number of standard deviations, times the length of a standard deviation. X bar plus or minus z star sigma over root n. It's always our point estimate plus or minus our margin of error. So here we're going to get 24.5 plus or minus 1.645 times 0.5112. Over here, we're going to get 24.5 plus or minus 1.645 times 0.4427. That's the one we already did. And 24.5 plus or minus 1.645 times 0.3960. So I'm going to go to my calculator now and hit up all these guys right here. 1.645 times 0.5112, 8409. And I'm going to leave these in this format right here, by the way, rather than actually going all the way to the interval. I think the interval is better to literally see the upper and lower bound, but right now I just want to make an argument about how the margins of error changed right here. So I'm going to leave, I'm not going to go one step further right here and get my true interval right there. I'm just going to leave it in plus or minus form. 1.645 times 0.4427. That's the one that we already saw. So this will be 24.5 plus or minus 0.7282. And 24.5 plus or minus 1.645 times 0.3960, 0.65142. 1.6514. So the big takeaway that you should be seeing here is that as our sample size gets bigger, our margin of error gets smaller. And that makes a ton of sense, right? Margin of error is measuring how far off are we. If we collect more data, then we should be more confident that our answer is correct. We should have a lower chance of error out there, right? So it makes sense to me that as sample size increases, the distance away from our estimate that we think we could be should get smaller. We should have more and more information here because we have a larger sample size that increases our confidence about where our correct answer lives. So this is our effective sample size on our margin of error right there. We're watching the margin of error term get smaller and smaller and smaller as the sample size gets bigger and bigger and bigger. We're getting narrower intervals because we have more information. That's good. Next one here. Our population standard deviation is 2.8 points. What if it was 1.8 or 3.8 points? Well, we can kind of do the same thing in this guy right here. We can make our sigma equals 1.8, our sigma equals 2.8, and our sigma equals 3.8. In this case here, let's see, how do I phrase this up above? For all three cases, x bar is 24.5, n is 40, 90% confidence tells me z star is 1.645. And so I can form my confidence intervals here. Remember, x bar plus or minus z star sigma over root n. And here we're going to get a 24.5 plus or minus 1.645 times, and I'm getting a 1.8 over root 40. 24.5 plus or minus 1.645 times 2.8 over root 40, and 24.5 plus or minus 1.645 times 3.8 over root 40. All right? And again, what you should be able to see here before I even do any multiplication is that since this term that's changing sigma is in the numerator of the margin of error, as sigma gets bigger, the margin of error gets bigger. The more deviation we have in our observations, then the less confidence that we have that our answer is correct, right? That gives us more options of it being kind of further away out there. So 1.645 times 1.8 divided by the square root of 40 is giving me 0.4862. On the next 1.645 times 2.8 divided by the square root of 40, I'm getting 0.7283. That's the one that we already saw. And on the last 1.645 times 3.8 divided by the square root of 40, and that's going to give me 0.9884. And here we can make a very similar observation as we just made on the last one, except in this case, notice it's opposite. As standard deviation increases, margin of error increases. that says if our samples vary quite a lot, then we shouldn't just be trusting our point estimate to be a good estimate for mu. If our samples vary a lot, then we might want to be claiming a bit of a wider interval out there, and that's exactly described here. If we have more variation in our observations, sigma is large, then we should see a large margin of error surrounding our point estimate out there. Hopefully that kind of makes intuitive sense there. This last one's a really important one right here, and we're going to get a little bit more Excel computation going on here. I might hold off on the working backwards questions till tomorrow there. I think I will. So maybe let's just answer number 4 and summarize what we've seen here. The confidence level was 90%. Form 4 confidence intervals associated with an 80%, a 90%, a 95%, and a 99% confidence interval here. So in these cases, we still have that X bar is 24.5. We still have that sigma is 2.8. We still have that our sample size is 40, but now Z star is going to change. Maybe I should make this happen like this. Let's do our confidence. I'm going to make sort of like a table. My confidence is 80%, 90%, 95%, 99%. Let me do this. All right, so here's what we're going to do. From our confidence, I want to determine what is my upper tail area. From the upper tail area, I want to determine a Z star. Once I have Z star, I can go ahead and determine my confidence interval here. So I'm going to draw some pictures to help us out with this, since this is kind of one of our weirder things right here, right? That's not too bad. We just got to be confident with what we're doing here. So I'm going to draw my picture right now for our 80% confidence interval. If we're talking about an 80% confidence interval, then we are interested in where 80% of the area is symmetrically centered in the middle right here. That means to me then that the remaining 20% is evenly split between the two tails. 20% divided by 2 is 10%. My Z star value is always going to be this upper boundary between my middle blank percent and the upper tail percent right here. So what I'm going to do up here in my table is say, if we're looking at an 80% confidence interval, 100 minus 80 is 20. 20 divided by 2 is 10. 10%. There's my 10% right there. All right, so what I know that's going on up here is that my, what I should say, I'm gonna change this very slightly right here, what I'm going to name this column right here. Double, hang on. I gotta erase my 10 now also. Okay. So what I need to find Z star is I need to know how much area is to the left of Z star. So if I come over here, to see where Z star is, then you should notice that 90% of the area is to the left of Z star. The middle 80% plus one of the tails. So in an 80% confidence interval, there's 90% of the area is to the left of the Z value. And so I can come over here and get my, I'm going to call this guy Z star 90. Very importantly, Z star 80, and that's because the middle 80%, the upper bound of that has 90% to the left of it, so I'm going to do a equals norm dot in What is our probability? 0.9. Our mean is 0. Our standard deviation is 1. That gives me, that doesn't even make any sense. What? Oh, I got my mean and standard. Oh, wait, no, wait, right? What? Why is it giving me a percentage? I didn't get a percentage before. What does that even mean? Norm dot inverse. I'm giving it the probability of 0.9, a mean of 0, and a standard deviation of 1. I want to know how many standard deviations are we at if 90% of the area has been accumulated. What in the world is 128%? Why am I... Why is it giving me this as a percentage? So notice here, what's going on here? Format cells. This should be just a general number. That's really weird. It just changed my formatting for some reason. Format cells as numbers. General. Okay. That was very strange. I don't know why it was doing something wonky to me right there. In any event, I just found that my z-star value of interest is 1.28. That is a number of standard deviations away that we will be traveling to experience the middle 80% of our values out there. Okay, that guy got a little bit, we got a little hung up right there. We're back. So now we look at our 90% confidence interval. That's going to give us our middle 90%. That gives me 5% in either tail. My z-star value is always going to be my upper bound of that middle chunk right there. And so here we can see that 95% of the area is to the left of z-star. So 95% of the area is what is to the left of it. So I can come on over here now and say my z-star for a 90% confidence interval should be my norm.in probability 0.95. That's how much area is to the left, 0 and 1. This is the one we already did, by the way. That's our 1.645. And we can keep rolling here. Now, 95% confidence interval. That means that we're looking at our middle 95%. We want to know where its cutoff is, right? So we're going to get 95%. That means that there's 5% remaining in each of the tails. 5% divided by 2 is 2.5%. And therefore, if my z-star value is the upper bound of that cutoff right there, then it looks like 95 plus 2.5 is the area to the left. That's 97.5%. So 97.5% of the area to the left. And I can come on over here then and do my z-star 95. And that should be norm.in. I've got 0.975. That's 97.5% is the area to the left. 0, 1, because I'm in Z land. And I'm getting 1.96. And finally, let's set up our z-star for our 99% confidence interval. 99% confidence interval. We're getting pretty extreme now. Nothing's changing about what we're doing. We're just recognizing that like our tail area is getting to be real small out there. If it's 99% is captured in the middle, then that remaining 1% is shared between the two tails. So this is a 0.5% and a 0.5%. That means to me that if we're looking at our value of interest here, z-star, our number of standard deviations to hit the cutoff, that 99.5% is to the left of z-star. And therefore, I can come over here and get my z star 99, and that's going to be norm.in of 0.995. 0.995 is 99.5%. That's the area to the left of my location of interest. And that's going to give me 2.576. All right, so I found all my associated z-star values for all of my different confidence intervals here, and we could then form each of our confidence intervals. I'm going to kind of not write out all of our full responses here, but we've computed the changing value of interest here. I now have that my z-star is 1.282 times my sigma over root n, 2.8 over root 40. And we can do this for each of these guys here. 24.5 plus or minus 1.645. And what you can see is that since this is a multiplicative term, the z-star term that we're changing here, you should see that our margin of error is getting bigger and bigger and bigger as our confidence gets bigger and bigger. If you want to be 99% sure that you actually got mu in your interval needs to be wider to make sure that there's a very small chance that you missed. Right? So having high confidence is a trade-off. We generally prefer to have small intervals because those would be where we are very certain that we know the answer. But if we want to have high confidence, we have to make a big interval to be super confident that it's going to fall within that interval here. Right? So our conclusion here is the larger our confidence level gets, the larger our margin of error is going to get, because we have to cast a bigger net to be more sure, more confident that we're going to catch a fish. If we want to increase our confidence that we catch a fish, we have to increase the breadth of our net. So again, I'm kind of stopping here a little bit short of actually forming a lower bound, upper bound confidence interval here, but certainly we can kind of see the piece that's changing right here, and very important, you guys can see where are we getting these values. I think these pictures are like the super important ones for us to kind of take away from this here today, finding that we can find z star, our location of our number of standard deviations of interest to capture a middle percentage, is always going to be 100 minus the middle percent of interest divided by 2. And we're always dividing by 2 because there's always one of our tails is accounted for in the area to the left of z star, but one of our tails is not because it is up above. And remember that Excel is always doing our area to the left computations. That's why we're setting ourselves up with these types of statements that we're making right here. So as promised, I do want to come back up to our kind of conclusion page up here and kind of re-go back through what we went through now that we did some computations. Come on, where are you at? Holy cow, we wrote a lot today. So our best guess from you is X bar. So what you've seen is that our sample average, what was 24.5 in all of our examples today, that was where we centered everything. All of our confidence interval statements say X bar plus or minus and some stuff. If the population has a large standard deviation, it will make the interval wide. We saw that increasing sigma increased our margin of error, the distance from the center to the edge. The more individuals we sample, the more confident that we are that a sample average is reflected the population average, so the larger n should mean a smaller interval. And notice here, I'm going to scroll down and show our equation right here. We have our general equation that looks like this guy right here. Notice that z star, as it gets bigger, this whole margin of error gets bigger. As sigma gets bigger, the whole margin of error gets bigger. But as n gets bigger, the margin of error gets smaller because we're dividing by the square root of n right there. So this is kind of just our easy way to remember this, is that this is really like both of these are numerator terms, z star and sigma. Square root of n is a denominator term. So if our confidence gets larger, or if our standard deviation gets larger, the margin of error gets larger, and therefore our entire interval gets larger. If our sample size gets larger, then the margin of error gets smaller because we're dividing by the square root of n, and therefore our entire confidence interval gets narrower. So that says collecting more information, a larger n, is good. It's going to squeeze down your confidence interval to be a much narrower interval of interest. So what are we going to do tomorrow? Well, tomorrow we're going to do two different things. One of those things that we're going to do is we're going to come back to this question right here. You should notice that this question is about a confidence interval of a population proportion rather than a population average like we only looked at today. Notice today also we only worked in a scenario in which sigma was known, but as we discussed last week, it's pretty rare that we know sigma, but that we don't know mu. So what we're also going to do tomorrow is we're going to update this z stuff that we just did to instead look at our t distribution, which is more appropriate when we don't know the true population standard deviation, which is a lot more common. So just like last week, we saw that we had a z test, a t test, and a prop test. We're going to have a confidence interval for averages when the sigma is known, the z. We're going to have a confidence interval for when sigma is not known, that's t. We're going to have a confidence interval for proportions. That's our P stuff right there. So we're going to get a matching confidence interval to go with the same three scenarios that we saw last week. The only other thing I want to hit tomorrow, other than changing from Z to T into P, is do a little bit of working backwards problems. If I give you a confidence interval, can you backwards solve for what the point estimate must have been and what the margin of error must have been? This one will be pretty easy. This one's a little bit harder, but I think is much more meaningful for true statistical situations. This question says, how many people must we sample to get a margin of error down to a certain error? This is super important for polling. When pollsters go ahead and sample people, what they want to do is they want to have a small margin of error. And so what their boss might say to them is say, hey, listen, I need you to go sample the support for this candidate and get it down to a margin of error of 1.5%. Well, if you're doing the polling, then you're going to need to figure out, well, how many people am I going to have to sample if I'm going to get a margin of error of 1.5%? You might need to go and sample more people or realize that you can just get away with sampling just a couple. Knowing what your desired margin of error is can allow us to deduce how large of a sample we must take to get results that are satisfactory to us here. So this is actually, although I refer to this as like working backwards, this is honestly one of the more common confidence interval computations that's ever done in the real world, is saying, how much data do I need to collect so that I can be exactly this certain about an estimate that I'm making right here? Hopefully you realize that that's kind of a pretty natural question to ask. How much data do I need to be this confident about a guess that I'm making? That's a pretty natural question to ask. So we'll hit up these working backwards questions tomorrow, and we'll also look at, rather than just talking Z stuff like we did today, Z stars are everywhere, tomorrow we're going to see some T stars, and our proportions are going to be estimated by a normal probability. So for our proportion estimates, we'll be back to Z star again, but we'll see our three total cases. Today we just looked at one scenario, just like last week on the first day we looked at one scenario and then we expanded to our three scenarios. We'll get those exact same three here tomorrow as well. So I'm going to go ahead and wrap it up for today. Tomorrow we've got confidence intervals when we don't know sigma, confidence intervals for proportions, and solving for some components of pre-existing confidence intervals. So sort of some working backward steps right here. That's all for me.